All right, Unit 3. This is the review for Exam 3. This covers sections from Chapter 4 and Chapter 5. Chapter 4 deals with exponentials and logarithms. Chapter 5 gets into integration and finding antiderivatives. So question 1, these questions are from 4.2 and 4.4. We're trying to find derivatives of exponential and logarithmic functions. So what we're doing here on question 1 is we're using the rule, the derivative with respect to x of e to the u is equal to e to the u times u prime. So this is our u function here. So the derivative of e to some power is equal to e to that power multiplied by the derivative of that power, which is 4x so 4x times e to the 2x squared. Question 2, the rule we're using here, the derivative with respect to x of the natural log of u is equal to 1 over u times u prime. And this would be considered our u function there. So we've got 1 over u times the derivative of u, or u prime, we've got 8x over 4x squared. 8 divided by 4 is 2, and then x divided by x squared leaves an x on the bottom, so we've got 2 divided by x. Now question 3 and 4 are from section 4.2, so it's using the same idea as this rule here, that the derivative of e to the u is equal to e to the u times u prime. But we're going to incorporate some other rules of derivatives, the product and quotient rule. So for question 3, this is a quotient, so we're going to use the quotient rule, obviously. So y prime so if you recall the quotient rule, low d high minus high d low, all over low squared. So low times d high, so the derivative of the upper function. And since here we have the upper function is an e to the u situation, so the derivative of e to the u is e to the u times u prime, so we've got e to the u times u prime. So we have, this is low right here, this is d high, so low d high minus high times d low, so that's going to be 20 x to the third, all over low squared. If we look at the numerator and try to factor out a common factor, it looks like we have a e to the 2x to the 5th power is a common factor. Looks like we can factor out a 10 x to the 3rd from that. So our common factor in the numerator is going to be 10x to the third times e to 2x to the fifth. That's our common factor in the numerator. So if this term here is taken or factored out of this left side of the numerator here, that's going to leave an x and a 5x to the fourth plus 4. Now, when this term here is factored out of this side, looks like we're going to have just a 2. And then we have the denominator, 5x to the fourth plus 4 squared. So let's see what we end up with here. In the numerator, 10x to the third times e to the 2x to the fifth. This little piece left inside looks like it's going to simplify to a 5x to the fifth plus 4x minus 2 all over 5x to the fourth plus 4 squared. Now over here for question 4, this is going to use the product rule. We have 3x to the fourth multiplied, there's a multiply sign there, multiplied by e to the 5x squared. So this is an f prime g plus g prime f situation, just product rule. So the derivative of the first factor of the product, so f primes, that's going to be 12x to the third, so f prime times g plus g prime. So now we need the derivative of the second factor there of the product. So the derivative of e to the u is e to the u times u prime. So this here would be the g prime part of the product rule. Now we need the f function times 3x to the fourth. So this plus sign here separates that into a left and a right side. So we want to see what they both have in common. They have an e to the 5x squared in common. Well, let's simplify this a little bit more before we start factoring out. So y prime equals 12x to the third times e to the 5x squared plus 30 x to the fifth times e to the 5x squared. So we have an e to the 5x squared in common. Looks like we could factor out an x cubed. And between a 12 and a 30, looks like we could factor out a 6. So 6x cubed e to the 5x squared. That's going to leave a 2 plus 5x squared. Honestly, I'd be okay with either one of these two forms here. I'd be okay with either one of them. For question 5, these 5 and 6 rather come from section 4.4. where we're not just finding the derivative of a logarithmic function, but we're also applying properties of logarithms before finding a derivative. So what's going to have to happen here in question 5, if we are using the rule the derivative of the natural log of u is equal to 1 over u, that's ultimately what we're getting at, except we don't want to use this as our term for u. That's going to be pretty confusing to find u prime. So what we want to do is simplify this here a little bit using the properties of logarithms that we talked about. So starting with this exponent, we can move it down in front of the logarithm. So we're not even taking derivatives yet. I'm just rewriting the equation y equals 5 times the natural log of this whole thing. And then another property of logarithm states if you're taking the logarithm of a quotient like this, you can separate it into multiple logarithms using subtraction. So y equals 5. Now it's important that you multiply 5 to the whole expansion, so that's why I'm using a parenthesis. So natural log of the numerator minus the natural log of the denominator. And if we want to distribute the 5, okay, now we can take a derivative using this rule here. So we're going to take the derivative separately. We have a left side and a right side. So now if we take the derivative of this natural log expression, it's going to be 1 over u, or 1 over 3x to the 5th times u prime, which is going to be 15x to the 4th. Now we can look at this side here, so it's going to be minus 5 times, now we can do the derivative of this natural log expression, which is 1 over u, or 1 over 2x to the 3rd plus 5 times u prime, which is 6x squared. So multiplying all of these terms into the numerator gives us 75x to the 4th, rather, over 3x to the 5th minus 30x squared over 2x cubed plus 5. We can simplify this fraction here. 75 divided by 3 is 25. X to the 4th divided by x to the 5th leaves an x on the bottom. So I've got 25 over x minus 30x squared over 2x cubed plus 5. Question 6, actually a lot like question 5, uses the same rules here. The derivative of natural log is 1 over u times u prime. We're going to have to expand this logarithm using pretty much the exact same properties. So we don't like these roots with logarithms or derivatives really, so we're going to change these into exponents. So y, instead of a cube root, that can be raised to the 1/3 power. And then we could do the same thing. We drop the 1/3 down in front. Actually, I'm missing a logarithm. There we go. Y equals natural log of that to the 1/3 power. So now we could drop the 1/3 power in front of the logarithm. And since we have a quotient, we can expand the logarithm into two logarithms using subtraction. So natural log of the numerator, subtract natural log of the denominator, and then distribute the 1/3. Now we can start doing the derivative. The 1/3 is a coefficient, so it still stays a coefficient of the derivative. Now we do the derivative of this natural log expression, which is going to be 1 over u times u prime. And then this 1/3 coefficient, derivative of that natural log expression there is again 1 over u times u prime. Simplifying, we're going to have 12x squared over 12x cubed. And then the 3 here and the 12, that can make 4. X cubed over 3x to the 4th plus 5. And finally, the 12's cancel there to 1, and x squared over x cubed can become 1 over x. So final answer, 1 over x minus 4x cubed over 3x to the 4th plus 5. Question 7 involves some of the applications of derivatives that we talked about in the first unit, finding the equation of a tangent line. So slope-intercept form, if you remember, is y equals mx plus b, so we got to have that slope, and the slope comes from the derivative using a particular x value there. So first step here is to find y prime, that's the derivative. So y prime, and this is an e to the u situation, so the derivative of e to the u, remember, is e to the u times u prime, and the derivative of negative x plus 1 is negative 1. So the derivative is y equals negative e to the negative x plus 1. So now what we need to do is use our x value of negative 2. So at x equals negative 2, y prime is equal to negative e to the negative 2 plus 1, which is negative e to the negative 1, or remember, when you have a negative exponent, then the term can drop to the denominator and have a positive exponent. So this is negative 1 over e. So that's our slope. Well, that's the slope at x equals 2. So we're going back here to this y equals mx plus b. We know the slope now. The slope is negative 1 over e. We haven't been given this value for b. So what we can do is use the x and the y value given to us here with this point. X equals 2, y equals 1 over e. So we can set up an equation here. So using this function here for y, we can use the value there, 1 over e. So 1 over e equals our slope times the x value here of 2 plus the unknown y value, or the unknown b value rather. And then just solve the equation. Looks like we have a b value of 3 over e, so the equation of this tangent line at the point 2, 1 over e is y equals negative 1 over ex, that's our slope, negative 1 over ex plus 3 over e. Alright, question 8 is from a couple of different sections, primarily 4.4, because we're practicing still taking derivative involving some natural log functions there. The natural log of 2y cubed right here. But we're going back to something from Unit 1, implicit differentiation. The reason this needs to be done implicitly is we're finding the derivative with respect to x, but our expression here, our equation, has some terms, some y terms, so we need to use implicit differentiation, which is really just the chain rule. We have outside function here, something being squared, and then y is an inside function, so we have to use a chain rule for that. So we're going to take the derivative of each term individually. So starting with this first term here, the derivative of 4y squared is 8y, but that's just taking the derivative of the outer function here with the squared. So now we need to take the derivative of the inner function y, which is dy dx. Now we move on to this term here. Natural log, the derivative of the natural log of u. So remember, the derivative of the natural log of u is equal to 1 over u times u prime. So if we take this derivative, we're going to have 1 over u times the derivative of u. So this is u, so we're going to do the derivative of u, which is 6y squared, but because we have a y term and we're taking the derivative with respect to x here, we've got to do a dy dx. Now we move on to this last term here, 7x. The derivative of 7x is just 7. So simplifying, combining some like terms, first term can just stay 8y dy dx. This term here, the one in the middle, we can simplify a little bit of that. 6 divided by 2 is going to be 3, and then a y squared over y cubed would leave a y on the bottom. So that can simplify to 3 over y dy dx equals 7. Now both of these terms have a dy dx which I can factor out. So dy dx factored out is going to leave an 8y plus 3 over y. Now it's going to be easier if I combine this into one term. 8y plus 3 over y, if I combine that into one term. So I can do that by getting a common denominator. Since this is a fraction, I've got to make this into a fraction, so I can put a y in the denominator and multiply it by another y in the numerator, like that. So I'd have 8y squared over y plus 3 over y. So combining that, I would have 8y squared plus 3 all over y. So now I want to get this dy dx all by itself, because I want to end up with dy dx equals. So that means this term here has got to move over to the side. So since this is a fraction, one way you can move a fraction to the other side of an equation is to multiply by the reciprocal. So if I were to multiply this by y over 8y squared plus 3, if I multiplied that by its reciprocal, it would cancel out. So I'd end up with 7y over 8y squared plus 3. Questions 9 and 10 come from section 5.1. Chapter 5 is when we started talking about finding antiderivatives, which is the opposite of finding a derivative. It uses techniques of integration. 9 and 10 particularly are finding what's called a particular solution. That's why we've been given an initial condition. Instead of having a plus c at the end of the antiderivative, we're going to find the particular value for c. So what we need to start with is finding the antiderivative of this term right here. So I'm going to rewrite it. F prime of x is equal to x to the 1/2. You have to integrate using exponents and not radicals. And now this is just an example of the power rule. We add 1 to the exponent and then divide by it. So f of x is x to the 3/2, and then you would divide by 3/2, but rather than dividing by 3/2, it's a little easier to multiply by 2/3, and then, like I said, initially we're going to have this plus c, but we need to actually find the value of that c using these values here. When x equals 9, then f of x is equal to 4. So just replace it. 4 is equal to 2/3 times 9 to the 3/2 plus c. Now c is the only unknown. So 9 to the 3/2, first we deal with the bottom number of that rational exponent. That means it's a square root. The square root of 9 is 3. And then we do the top number of the rational exponent, which is raising it to the 3rd power. 3 cubed is 27. Now we can divide 27 by 3. 27 divided by 3 is 9. And then we can multiply it by 2 to get 18. Hopefully you followed that. If not, you can certainly use a calculator, but we get 18 out of that. So 4 is equal to 18 plus c, which means that c is equal to negative 14. So coming over here, we have f of x is equal to 2/3 times x to the 3/2 minus 14. One way you can check this is to plug in your initial condition, and you should get a 4 if you plug in a 9 for x. So it's one way you can check. Now moving over here, question 10, exact same thing. Just different kind of function. We have a linear function, but it's still going to use the power rule. So we need to find the antiderivative. So we need to integrate 4x plus 2. So we're going to get 4x squared over 2 plus 2x plus c. And simplify the coefficient of x squared to get 2x squared plus 2x plus c. Now we use the initial condition. That's our x value. That can be our f of x value. So we have f of x is equal to 1, and all the x's are equal to negative 2. And then find c. So here, negative 2 squared is 4. 4 times 2 is 8. And then 2 times negative 2 is 4. And then here 8 minus 4 is 4. So c is equal to -3. So the particular solution is f of x, well, I'm gonna run out of room there. Guess we can write it on the bottom. F of x, 2x squared plus 2x minus 3. Now 5.2, we started looking at some more difficult integration techniques of integration, still applying the power rule, but now we started doing the backwards chain rule, I guess you could say. We were undoing the chain rule, which means we needed to have a u and then a u prime or a du, u being the inside function, and then du being the derivative of that inside function. For example, here on question 11, we have an inside function here, x to the third minus 2, so we could call this our u function. And then we have the derivative of that inside function here, du. So if we let u equal x to the third minus 2, then the derivative of u is equal to 3x squared times dx. So we've got the 3x squared and the dx, so that can all be replaced with du, and then this inside function here can be replaced with u, so the whole entire problem can be rewritten as u cubed times du, the integral of u cubed du, which we now can apply just the power rule, making it u to the fourth divided by 4 plus c. Now we go ahead and take out the u substitution and put back in the value of u, which was u to the third minus 2 to the fourth power divided by 4 plus c. This is called indefinite integral because we aren't worried about what the value of c is like we were in the problems before. Pretty much the same idea on number 12, except I'm going to rewrite it. Remember, we don't really like radicals when we're dealing with integration, so the integral of 45x squared, and now I'm just going to use power of 1/3. So again, we have an inside function because it's being raised here to a power of 1/3. So I'm going to let u equal 5x cubed minus 1, which means du is going to be 15x squared dx. Now we've got the x squared dx, but it's supposed to be 15, and we've got a 45. Luckily, 45 is a we can make 45 some of the factors. We can split it up into 15. 15 times 3. So if I change 45 into 15 times 3, I could move the 3 out and leave the 15 there. So now I can rewrite the integral as 3 times the integral. So this is going to be replaced with u to the 1/3, and the 15x squared dx is going to be replaced with du. And now we use the power rule of integration. We add 1 to the exponent. So 1/3 plus 1 is 4/3. And then we can divide that by 4/3, or we can multiply it by 3/4. plus c. And then 3 times 3/4 is 9/4. Then we undo the u substitution. U was equal to 5x cubed minus 1 to the power of 4/3 plus c. All right, question 13. This is from section 5.3. Still using antiderivatives, or finding antiderivatives, but now we're using the exponential rule and the logarithm rule. So, question 13. What we're going to try to do is set up a situation where we have, let me get a pencil out here, where we have du over u. That's what we're going to try to set up. Because if you remember, the integral of du over u is equal to the natural log of the absolute value of u. So that's the situation we're going to try to set up here. So that means this bottom part here, we're going to let equal u which means the du, or the derivative, is equal to 6x dx. So in the numerator, we have 18x dx. We're pretty close to the 6x dx that we need. What I'm going to do is break up this 18 into a 6 and a 3. So I'm going to rewrite that integrand as 3 times the integral of 6x over 3x squared plus 4 dx. So now if you look, I've got the 6x dx in the numerator, and then the 3x squared plus 4. So what I've set up now is a situation where I've got 3 times the integral of du over u. And if we use this definition right here, the integral of du over u is equal to the natural log of the absolute value of u. And then we go back and unsubstitute for u. U is equal to 3x squared plus 4. Question 14. What we're going to try to set up here, since we already have the exponential term there, we're going to try to set up a situation where we have the integral of e to the u du is just equal to e to the u plus c. So here we're going to have our e to the u term, so u is going to be the exponent there of the exponent term, so u is going to equal x to the third plus 4, which means that du is equal to 3x squared dx. Now I've got the x squared and the dx right here, but where that 6 is, I should have a 3. So what I'm going to do is split up this 6, the negative 6 rather. I'm going to leave the 3 in here and put the negative 2 out there, because negative 2 times 3 is equal to negative 6. I'm going to rewrite that as negative 2 times the integral of 3x squared times e x to the third plus 4 dx. Now I can do my u substitution. This term right here, e to the x to the third plus 4, I'm going to rewrite as e to the u. And then the 3x squared dx, I can replace that with du, and then this can follow that definition now. The integral of e to the u du is equal to e to the u. So let's see, this is going to equal negative 2 times e to the u plus c. and then go ahead and substitute u back for x to the third plus 4. So this is e times x to the third plus 4 plus c. So it looks like 15 is a lot like number 13. What we're going to try to do is set up another situation where we have du over u, because that's equal to the natural log of the absolute value of u plus c. So again, I'm going to let that denominator term equal u. So if you take the derivative of that, du is equal to 25 x to the fourth dx. So I've got the x to the fourth and the dx in the numerator, but where this 75 is right here, I'm supposed to have this 25. So again, I can just break up that 75 into 25. I'm also going to pull that negative out and put it as a -3 out in the front, like that. So I can rewrite that as -3 times the integral 25x to the fourth, and then the denominator is 5x to the fifth minus 4. So now in the numerator, I've got the 25x to the fourth dx, that's going to become my du term, and then the denominator, I've got my 5x to the fifth minus 4, that's my u term. So I can rewrite this as -3 times the integral of du over u, which is -3 times the natural log of the absolute value, 5x to the fifth minus 4 plus c. And then it looks like 16 is going to be a lot like number 14. We're going to set up another situation where we have the integral of e to the u du is just equal to e to the u plus c. So this is going to be my u term, so I can set up an e to the u situation. So u is equal to x squared minus 5 du can be 2x dx. So I've got the x and the dx for my du term, but the 6 should be a 2 to match with that 2 there. So I'm going to rewrite the 6 as a 2 and then put a 3 out in the front. So it's going to be 3 times the integral of 2x e to the x squared minus 5 dx. So now the 2x dx can be rewritten as du, and this x squared minus 5 can be written as u. So this turns into 3 times the integral of e to the u du, and then we can use that definition up here. So we have 3e to the u plus c, and then substitute u for x squared minus 5. So now a new section, the fundamental theorem of calculus. We discussed that now putting these lower and upper limits of integration on the indefinite integral makes this a definite integral. What this is finding the area underneath the curve of the graph of this function. So underneath the graph and above the x-axis, this would be finding the area. We don't have to graph this and show the area, we just have to evaluate the definite integral using the fundamental theorem of calculus. So this is, let's see, let's first find the indefinite integral here, or the antiderivative, rather. So what it looks like we're going to do is move this term up to the numerator by changing the value of that exponent to -2. So I'm not going to worry about these limits of integration here. I'm just going to say that the integral of 5 over x squared minus 2 squared, I'm going to rewrite that as the integral of 5 times x minus 2 to the -2. Then I'm going to go ahead and pull the 5 out. Oh, we actually need the dx there. So since we have an inside and an outside function here, we really need to check that we have all parts of the chain rule. So I'm just do a quick u substitution. If u is equal to the inside function x minus 2, then that means du is the derivative of x minus 2, which is 1 dx. I've got the dx here and the 1 right here. So everything's there that should be there. So I'm going to go ahead and do my u substitution. This is just going to be u to the -2 du. And then if we do the general power rule, remember you add 1 to the exponent. And then divide by that exponent. So I'm going to go ahead and unsubstitute for the u. U, remember, was x minus 2. So we have -5 times x minus 2 to the -1. And now we need to evaluate that antiderivative with our limits of integration, which were between 3 and 5. And now we need to plug these limits of integration into the antiderivative, starting with the upper one here. So the 5 just goes in place of the x. So I'm going to write this as -5 times 5 minus 2 to the -1. And now we subtract the antiderivative at the lower bound. So -5 times 3 minus 2 to the -1. So this is -5 times 3 to the -1 plus 5 times 1 to -1. This term here, 3 to the -1, that's 1/3. So this is -5/3 plus, and then this term here, 1 to the -1 is just 1. 5 times 1 is 1, or 5. And this is equal to 10/3. All right, for number 18, we're going to try to set up a e to the u du type situation and find the antiderivative using that rule. So I'm going to let this here equal to u. So forgetting about these bounds and limits of integration, we're just going to do the integral of -2 e to the 2x plus 6. If I let u equal 2x plus, well, I need a dx there, 2x plus 6, then du is equal to 2 dx. So I've got the 2 dx, I just need to move that minus sign out in front. So I can rewrite this as negative integral of 2 e to the 2x plus 6 dx. That can be rewritten as e to the u du, which can be rewritten as negative e to the u which is negative e to the 2x plus 6. So now that needs to be evaluated using our bounds here, negative 6 to negative 3. So starting with this upper bound, plugging these in, we're going to get negative e, and then if that negative 3 goes in there, for the x, we're going to get negative 6 plus 6, and then we're going to subtract the antiderivative at the lower bound, so that's negative e, and then if that negative 6 goes in there, times 2 is negative 12 plus 6, so that's negative 6. Here we get a 0, e to the 0 is just 1, times the negative 1 there, so we're going to get negative 1 plus e to the negative 6, which is negative 1 plus, and since this has a negative exponent, this whole term is going to be written on the bottom of a fraction. Okay, we're getting there. 5.5. You can find the area bounded by two graphs using the fundamental theorem of calculus. So number 19 is dealing with this first topic here. So what we're talking about, the area bounded by two graphs, we may have a situation like this where we have a parabola and then some kind of a cubic function like that, and we need to find this area in between the two graphs. That's what it means by an area bounded by two graphs. So what we need to figure out first are what are the bounds of integration between what and what. And the way that we solve that is by setting these equations equal to each other, because graphs intersect when their equations are equal to each other. So we need to set the equations of these functions equal to each other and solve for x. So this needs to equal that. So the equation x to the third minus 4x is going to be set equal to negative x squared minus 2x. I'm going to get one side equal to 0, so I'm going to move all of these terms over here to that side. So add the x squared, and then add a 2x, so that's going to make that into a negative 2x. Now the right side is equal to 0. On the left side, you can factor out an x. And this can be factored further into x plus 2 and x minus 1. So we have three solutions to this equation. X equals 0, x equals negative 2, and x equals 1. So actually what's most likely happening here, since there's three different solutions to this equation, what's most likely happening is we have this third degree graph here from x to the third minus 4x. Whoops. And then we have this upside down parabola there with negative x squared that maybe looks something like that, some kind of upside down parabola. And that's a terrible way of drawing it here, but again, I'm just guessing. So we have actually two areas being bounded. We may have something like that and something like this. So there's two separate areas, because knowing that we have three solutions to that equation means we have three different points where the graph intersects with each other. So we're going to have to find an integral from here to here and another integral from here to here and add them together. That's looking like what's going on here. So one thing that's really important when doing these is to figure out which one is the above function and which one is the below function. Because you can see if I try to do this in different colors here, red. So this parabola, for example, that I'm outlining in red, between here and here it's the below function, but then between here and here it becomes the above function. And then let's do gray. This other one, from here to here it's the above function, but then when we go from here to here it becomes the below function. So let me erase this. Let's say that we're going to call this one function f. And we're going to call this one function g. So we've got to figure out, is f above g or is g above f at which point in this problem? So between let's say between x equals -2 and x equals 0. Again, I'm going to call this the f of x function. I'm going to call this one the g of x function. So what I need to do is choose a point in between -2 and 0. -1, for example. So I'm going to test f of -1 and g of -1 and see which one has the larger value. Whichever one has the larger value means that's the above function or the function on top between x equals -2 and x equals 0. So f of -1, if I plug it in there, becomes -1 cubed minus 4 times -1. Well, that makes a -1 here and a positive 4 there. -1 plus 4 is 3. Now for the g function, if I plug it in here, I get the opposite of -1 squared minus 2 times -1. Well, -1 squared is 1, but then multiply it by that negative, so it's -1. -1 plus 2. -1 plus 2 is equal to 1. So that means this one, since it had a higher value as the top function, that one's the bottom function. But that's just between -2 and 0. If we do this again for between x equals 0 and x equals 1, we've got to choose a test point in between 0 and 1. We don't have a lot of options, 1/2 for example, so we need to choose f of 1/2 and g of 1/2. So this is going to be 1/2 to the third minus 4 times 1/2. This one's going to be negative 1/2 squared minus 2 times 1/2. So here we're going to have 1/8 minus half of 4, which is 2. Here we're going to have 1/2 squared, which is 1/4, so that makes that -1/4. minus 2 times 1/2, so that's minus 1. So 2 is just 16/8, so 1/8 minus 16/8 is negative 15/8. And then negative 1/4 minus 1, 1 is 4/4. So negative 1/4 minus 4/4 is negative 5/4. So negative 15/8 and negative 5/4. Negative 15/8 is more negative, so that's a smaller value than negative 5/4. So now this one's actually the larger value here. So this one's become the top, and that one's become the bottom. And the reason that matters is when you're finding the area bounded by two graphs, the area in between two graphs, it's the integral of the top minus the bottom. So coming over here, the first integral, which was from negative 2 to 0, we need the top minus bottom. So looking back to our value between 0 and 2, it looked like f was our top function, so I need f of x minus g of x dx. But between 0 and 1, it switched. Now g of x became the top function, so now I need g of x minus f of x. And we're going to add these two. So this is what we need to solve for. So we need to do f of x minus g of x. So f of x minus g of x is going to be x to the third minus 4x, and I'm going to subtract g of x, which is negative x squared minus 2x, so this becomes x to the third minus 4x plus x squared plus 2x. So x to the third plus x squared minus 2x. So that's f of x minus g of x. Now if we do g of x minus f of x, this is going to be negative x squared minus 2x minus x to the third minus 4x. That's going to be negative x to the third minus x squared. And then that's going to be a positive 4x minus the 2x, so that's going to be a plus 2x. So now I can make substitutions here. This first integral, the integral from negative 2 to 0 of f of x minus g of x, that's this term right here. So that's going to be x to the third plus x squared minus 2x. So that turns into x to the fourth over 4 plus x to the third over 3 minus, well, it's really minus 2x squared over 2, but the 2's are going to cancel, so I'm just going to write that as x squared, and that needs to be evaluated between negative 2 and 0. So you do the upper bound here first, the 0. So that's going to be 0 over 4 to the fourth plus 0 over 3 to the third minus 0 squared. So that's the antiderivative of the upper bound. Now we subtract the antiderivative of the lower bound. Well, actually I just made a little bit of a, we don't need those parentheses, because the whole thing isn't being raised to the third power, it's just the numerator. So it's just 0 to the fourth and 0, there we go. So now we're going to have negative 2 to the fourth over 4 plus negative 2 to the third over 3 minus negative 2 squared. So this little piece here, 0 plus 0 plus 0, that just goes to 0. And then 2 to the fourth power here is 16 times negative is negative 16 over 4, so that's negative 4, and then that's a 3 right here. So the negative 2 to the third is negative 8 over, so that's negative 8/3, and then we've got negative 2. Actually, you know what, that's negative 2, that's positive 4. And then negative 2 to the squared is 4, so that's minus 4. So these actually cancel each other out, and then we've got a minus, a negative, that's plus. Let's try that again. That cancels with that. We've got a plus, a negative, so that equals 8/3. So now we need to do the other integral, this one here, from 0 to 1. The integral of 0 to 1 of g of x minus f of x, which we found right there. So it's negative x to the third minus x squared plus 2x dx. So the antiderivative is x to the 4 over 4, or negative x to the 4 over 4 minus x to the third over 3 plus 2x squared over 2, but the 2's there would cancel anyway, so that's just going to be x squared over 2, and that's evaluated between 0 and 1. So we do the antiderivative at the upper bound. So that's 1 to the fourth divided by 4, and then 1 to the third divided by 3 plus 1 squared, which is just 1. And then the lower bound 0, we're just going to have a 0 for that x and a 0 for that x and a 0. So we're just going to be 0 minus 0 plus 0, which is just 0. So here we're going to have 1 to the fourth divided by 4. That's just going to be a negative 1/4. And then we're going to have a minus 1/3 plus 1. If we put everything in terms of 12ths, that's negative 3/12 minus 4/12 plus 12/12. That equals 5/12. So now we need to add the 8/3 to the 5/12. So that's the same as 32/12 plus 5/12 equals 37/12. Okay, finally number 20. This is an application from section 5.5. We're finding the area between two curves. So we've been given two functions here, a demand and a supply. We've got the demand function here, and we have the supply function graphed here. And the point at which they meet, the point of equilibrium, that gives us the market price and the quantity. So if you look at the way that this axis is set up, here we've got the x-axis is quantity, here the y-axis is price. So the point at which these meet gives us a quantity and a market price, the point of equilibrium. So that's our first task, is to figure out what this point of equilibrium is. What's the x and the p coordinate? So easy way to find that, just set the two equations equal to each other. So first step, find the equilibrium so we have 200 minus 0.2x equals 50 plus 1.3x. Getting equations and variables and things on the same side, or numbers and variables on the same side, we're going to have 150 equals 1.5x, which means that x equals 100. So we know the quantity of that point of equilibrium, it's 100. That's the x value there. Now we need this p value right there. So if we choose one of the equations, supply for example, if we choose this supply equation, we get p, which we don't know yet, p equals 50 plus 1.3 times 100. That makes, this here makes 130. If you add 130 to 50, you get p equals 180. So the market price, or the price dictated by supply and demand, that whatever this goods that's being sold here should be sold for, is $180. Now let's start with consumer surplus. Consumer surplus is this area here. It's below the demand function, but above this line of $180. Consumer surplus, if you remember from our discussion, consumer surplus happens when there's a difference between what a consumer is willing to pay and what they actually do pay. See, so this line represents what a consumer actually is willing to pay for this good, and then this equilibrium point is what they actually pay. So the equilibrium price, or the market price, is lower than what the consumer would be willing to pay for this product. So that results in consumer surplus. So if you remember from the problem above, problem 19, when we want to find the area under a curve or between two curves, we set up an integral. So let's do consumer surplus. So it's going to be the integral from 0 to 100, and we find 100 because that's the quantity value. Those are the two x values from 0 to 100. So the integral from 0 to 100. Now we need the top function, which is, if you look over here on our graph, the top function is the demand function, which is 200 minus 0.2x. And then we subtract the lower function, which is the price, 180. So this results as the integral from 0 to 100. 200 minus 180 is 20, so this is 20 minus 0.2x. So the antiderivative is going to be 20x minus 0.2x squared over 2. $20x minus, now 0.2 or 2/10, if we want to do some simple arithmetic here, 0.2, this fraction, 2/10 is really the same as 1/5. So 1/5 divided by 2 is 1/10. So 0.2 divided by 2 is 1/10 x squared. And we need to now do the fundamental theorem of calculus. So we have our antiderivative evaluated between 0 and 100. Now we need the value of the antiderivative at 100. So we're going to have 20 times 100 minus 1/10 of 100 squared. This is the antiderivative evaluated at 100. Now we subtract the value of the antiderivative evaluated at 0. If we were to plug 0 in for both x's of the antiderivative, we would just have 0 minus 0, which results in 0. So now just evaluating this, 20 times 100 is 2,000. 100 squared is 10,000. If we take a tenth of that, that's 1,000. So this is 2,000 minus 1,000, which equals 1,000. So the last part of this problem is calculating this area here. This is the producer surplus. So this occurs, this supply function represents the minimum price a producer is willing to accept for selling its goods. And you can see that the market price is higher than the minimum price a producer needs for selling its good. So this results in producer surplus. So since it's the area bounded by two curves, the upper curve in this case is going to be the market price, $180, and the lower curve is going to be the producer surplus, or the supply function, which is 50 plus 1.3x. I need to set up another integral problem. There's going to be same integral from 0 to 100. Now the top function was the market price, 180. Now we subtract the supply function, which is 50 plus 1.3x. So this results in the integral from 0 to 100. We have 180 minus 50, which is 130, minus 1.3x. So then the antiderivative turns out to be 130x minus 1.3x squared over 2. So if we evaluate and use the fundamental theorem of calculus from 0 to 100, we need to evaluate the antiderivative first at 100. So this is going to be 130 times 100 minus 1.3 not x times 100 squared over 2. Now we subtract the value of the antiderivative at 0, but again, that would result in 0. Now calculating the value of this, 130 times 100 is 13,000. And then here, 1.3 times 100 squared. 100 squared is 10,000. If you multiply 10,000 by 1.3, you get 13,000. 13,000 divided by 2 is 6,500. And 13,000 minus 6,500 equals 6,500. Now, incidentally, here's a quick and easy way to check your results. Because our demand and supply functions are linear, this results in triangles. This, for example, the consumer surplus, would be simply the area of a right triangle. So we could use the area of a triangle formula, 1/2 base times height. The base is 100, so half of that would be 50. And then the height would be the difference between 180 and the y-intercept there of the demand function. If we look at the demand function, has a y-intercept of 200, so this value up here is 200. So it's 1/2 base times height, so the height there is 20. 50 times 20 is 1,000, so just by way of geometry, the area of that triangle for the consumer surplus is 1,000. Looks like that's what we got. Yep, we got 1,000 right there. Now for producer surplus, same thing, we have a right triangle. The y-intercept of that was 50 between 180, so that means the height is 130. And the length of the base is 100, so 1/2 base times height is going to be 1/2 of the base, which is 50, times the height, which is 130. And this gives you 6,500. So a quick and easy way to check answers there for producer and consumer surplus, assuming that the demand and supply functions are linear.